So let me propose something. This is the title of my talk. As you see, neutrino, first, here, where should I?
Not working either?
Neither.
Man, doesn't like you, huh? This one's working.
No, okay. Okay.
Sorry.
Not
Not
spoil my.
spoiling.
Please,
Sorry.
please. Okay. So, during the past week, you have had a lot of wonderful talks from Pedro to discuss something else for me. I can go. Okay, I have a proposal. Pedro talked about neutrino, right? Then Dan, a very wonderful overview about the neutrino detection. And then yesterday, Javier talked in details about CCD. So all is covered. I am done. Yeah? We can skip this. I expect you agree with me. Carla, what do you think? Oh. Okay. So let me start talking about the CCD just like a piece of silicon, right? Of course, it's more than that, but let me starting just thinking this like a piece of silicon. The first question, in that case, is why neutrino detection with a piece of silicon? Okay, one possible answer is there are a lot of silicon on Earth. I don't know. Okay. 10 more minutes.
Yes, we give you more minutes.
Now? Now? Martin. And it's almost the last talk. Now, yes. No as good as before. More reason to avoid this talk.
No, continue.
Okay.
We tried.
Yeah. So this is one reason to use silicon. Of course, it's not the real reason, but you see the fraction of silicon on Earth is just almost the same as the universe dark matter mass energy content. Of course, just by casual. This is a reason because we have a lot of silicon, and that is also a reason to the silicon be cheaper. But let me talk about silicon in a different way. Let's assume that you have 5 silicon atoms. They are, no, I don't know. And they are far away from each other. Yes? As you start to get them closer, the electrons start to see each other. Even more, electrons start to see the other's nuclei. And they start to feel attracted, like in the human behavior. So in that case, if you are in this regime and you go to the left, you start with just a band for the energy of the electrons, and then it is split in two. Around let's say 5 Armstrong, we have 2 bands. That is a semiconductor. What it means? The valence bands is for the electrons that belong to a specific nucleus, but the conductive bands for those who are, let's say, free, right? In the CCD we are using, we are talking about fully depleted CCD, fully depleted charge coupled device. It is mean because the conduction bands is almost empty. We have all the electrons here, right? So, why is so important a low energy threshold? Let's see. Here, we have 1.1 eV between those possible bands. 1.1 eV Yes? Why is important? Okay, because there are a lot of physics to learn with these kind of detectors. The most of the reasons to look for neutrino were already given by Dan, Pedro, right? But just to put a few of them on the table, we have that we don't know if are there light mediators other than the W and C bosons. That is a very important question. Are neutrino and neutrino the same particles or two different states, two different helicity states? Do neutrinos have magnetic moment? Or are the neutrino interaction beyond the weak force? And the last one here is how we can use 7-channel, which is, you know, a standard model prediction, to learn more physics. So all of these reasons can take advantage of a very, very low threshold energy. Why? Why is low energy threshold important? 2 years ago, with Pedro Machado and other guys from Fermilab, we studied the sensitivity of a huge amount of silicon, 10 kilogram, which is a huge because one CCD is roughly 1 gram, to detect neutrino. And what we saw is what you are seeing on the right. Here you have too many different candidates, magnetic moment, light vector mediators, and it's also the 7. Standard model here means essentially coherent elastic neutrino nucleus scattering. And what we see here is the lower the energy, because the event charge is essentially the energy for us. There is a relationship between them. 3.7 electron volts is what we need to create one electron hole pair. So it means that the lower the energy, the higher the number of events we expect in our detector. So why silicon? Because it allows us to have a detector with 1 eV energy threshold. And if we can go to the eV range, we can take advantage of the cross-section of this event, because we expect a lot more event when the energy is as low as in the EV range. So let me say something about 7th channel. From the Dan talk, thank you, Dan, for sharing your slides, we have all this range to study neutrino. Let me focus on 7th channel. And you all know, in the 7th channel, we have neutrino with, let's say, 10, 50 MeV. And if you go like a neutrino with 1 GeV energy, you just see what you have in front of you. But as low as you decrease, a neutrino decrease your velocity, your energy, you start to see around, and you have a big panorama, and you, with 50 MeV, like a neutrino, you can see all the nucleus, and you can interact with all the neutrons at the same time, and that is the reason why 7 enhances the cross-section a factor 200. In quantum mechanics term, the lower the energy, the higher the wavelength, right? Okay. So, the cross-section for 7s, here, over here, goes like q to the square, and q goes like n. Forget about the 1 minus 4, whatever, because all of this part is very, very close to 0, and that is the reason why we said that this goes like n to the square. But I have a question for you. Why, if 7 has a cross-section 200 times higher than inverse beta decay, inverse beta decay was the channel to detect neutrino almost 70 years ago? Why? Why not 7s? 7 is not waiting for us. 7 is there, is the standard model. Do you know the answer? Energy threshold, this seems to be a problem of our detector, and of course it's related with that. The reason is that we in general confuse cross-section, the probability of interaction, with the probability of detection. It's something different. The probability for a neutrino to interact with our detector by the 7th channel is huge. 200 times higher than the inverse beta decay in the case of silicon. But for each of those interactions, the ones coming from the 7th, we have a very, very small amount of energy to measure. I will go in detail about that point. But in the case of inverse beta decay, Dan covered this pretty well, appears new particles, and the energy release is huge in comparison. And that is the reason because we can see inverse beta decay, and we can, but it's so hard to detect 7s, right? So, up to now, we have addressed a few questions. First, why I am talking about neutrinos in CCD on Friday after many wonderful talks. Then, why neutrino detection with silicon, right? The answer is because silicon has a band gap close to 1 eV. And why 1 eV is important for us? Because looking at this energy range, we can take advantage of increasing the number of events we expect for different beyond standard model. Also, even if we are looking for 7s. And then we discuss why 7 is so hard to detect. If the cross-section is 200 times higher, okay, but the probability of detection is not the same of the probability of interaction. But now, or up to now, I need to discuss why with CCD. Okay, let's back to CCD. This is from the Javier talk yesterday. He explained in detail what a CCD is and also what an skipper CCD is. I will take advantage also of the Javier talks. And just for you to remember, what we expect when a neutrino interacts with an electron is for that electron to have the energy to be promoted to the conductive band, right? And then we can go and see how many pixels has one electron, two, whatever. And the price to pay is just the energy the electron needs to move from one band to the other one. This is 1 eV, right? So small. Okay, how we can learn about the price to pay in average. When I said in average, we already performed this experiment. We irradiate CCDs with X-rays, and we have these nice histograms. And then, because the energy of the X-ray is very, very well known, we can divide that energy for the number of electrons we saw in the CCD, and we have the relationship between energy and electron. And this is roughly 3.75 eV per electron in average, right? Okay, now we understand how is the relationship between the energy and electron hole pair. But what happens if a neutrino interacts with the nucleus as a wall in the coherent elastic neutrino nucleus scattering? That is the case. Okay, under this situation, we have two prices to pay. The first one is the neutrino is a tiny particle, yes, and in the 7th region, in the KV region, is also a particle with, let's say, 10 or less MeV. So a silicon nucleus is something very, very big. So the energy transfer is very, very small just for kinematical reason, right? That is the first point. But the second one is even if we are able to detect the amount of energy released in that nucleus, the problem is that the nucleus is very, very inefficient to ionize electrons with the energy they have. That relationship is what we call the quenching factor. And just for you to know, for 1 keV energy, if a nucleus has 1 keV energy, just 10% of this we will use to produce electrons. So 90% of the energy would be like phonons, yes, and we cannot measure it with an skipper. Okay, so now we understand why 7 is so hard. But if we have a piece of silicon and we have a semiconductor with 1 eV band gap, we steal something else. We need a detector able to go to the sub-electron noise to see how many electrons are in each of those pixels, the one Javier talked yesterday. And the answer for that is the skipper CCD, which is a piece of silicon, it's a charge-coupled device, but with some very, very nice properties. Just one slide regarding this, because again, I am taking advantage of the previous talk. And here is the detector. This is 2 by 4 centimeters. Yes, it's a small one. The mass is around 1-2 grams. And the thickness is around 700 micrometers. And the result of using this, because of the very wonderful capability, which is this detector can measure the charge in each pixel as many times as you decide without destroying it. So at the end, you take the average and you can reduce the real noise until almost 0. It's negligible. So we have a sub-electron real noise, and that is the reason why we are able to observe how many electrons we have in each pixel without uncertainty. But not if we have 1, 0, 2. We are able to distinguish between 1570, 1571, right? So we have now the technology to go for event that release in our detector just 1 eV, right? Okay. During the done talk, you have learned about all the scales different experiments are using to go for neutrinos. And the lowest here is coherent in the kV scale. I need to move a little bit this on the right just to make a little bit of a space for our experiment here. In the EV range, we have the skipper, right? And with the skipper CCD, we are already performing an experiment to look for neutrino physics. Yes, and that is the second part of my talk. So up to now, what I expect from you is to fully understand why CCD, why silicon, why it's so important to have a very low threshold, and why we are interested in doing this kind of experiment. Right? Any question up to here? No? Okay. So, you know, to detect a neutrino is very, very hard. And the main reason is the probability for a neutrino to interact with matter is very, very small. So how we can compensate that? With a huge amount of neutrino. That is, in general, the way. Or a very, very big detector. Or both. Okay, in our case, we don't have a very, very big detector. We just have a huge amount of neutrino. Why? Because nuclear reactor produce a lot. Here on Earth, when you are close to a reactor, you have more neutrino coming from the reactor than coming from the sun, close to the reactor. So there is something especially I said wonderful for us, which is we have nuclear reactors in South America. Here in Brazil, there are 2, and there are 3 more in Argentina. So this is an opportunity for us, right? And we take advantage of that opportunity. Let me say how the neutrino flux looks like when they are producing a nuclear reactor. This is very different from the neutrinos we use, or the people from coherent collaboration use to see the coherent interaction, because this neutrino has a peak around 1 eV, MeV. Yes, instead of 25, 50, just 1 MeV. And please remember, this neutrino, we transfer just a little bit of that energy to the nucleus, and then the nucleus just use 10% of this to ionize. Okay, so this is, of course, South America, Argentina, and Brazil. And top on the right, you are seeing Angra 1 and Angra 2. And top on the right, bottom on the right, you are seeing Atucha 1 and Atucha 2, two reactors 100 kilometers away from Buenos Aires, the Argentine capital city. So, let me start with Angra 2. Now we are here, San Pablo. We are 230 kilometers away in right direction, but by car it's something like 5 hours, right? But it's close. This experiment, it's running very close. And this nuclear reactor is a nuclear power plant with almost 4 gigawatts. That is a lot, 4 gigawatts thermal power. The experiment, CONI experiment, is over there, just close to the wall of the reactor. It means 30 meters away from the center of the core, right? If you are there, you have a flux of almost 10 to the 12 neutrinos per second per centimeter squared. That is a lot, and that is what we need to observe neutrino because of the very, very low cross-section. Inside, when CONI started in 2016, the first detector were 16 megapixels fully depleted CCD, the pixel size, the one as I mentioned, and the shield we use is a passive one, no active veto, because there is a price to pay to have subelectron resolution. We still don't have good time resolution, right? Okay, just for you to know, here we have 30 centimeters of polyethylene, then 50 centimeters of lead, and then again 30 centimeters of polyethylene, which is roughly 16 tons of shield, right? From 2015 up to now, almost 10 years, CONI produced a lot of scientific results. You can go in details looking at these papers. I will put attention on this, the one from 2020, and the last installation of a new detector. Why I will go over this? Because I will also take advantage that the most of you have taken a very, very wonderful course about statistics this week, right? So you all know how to produce an confidence level, an upper limit, and an exclusion limit like this. So CONI, which is still not able to see the coherent interaction, was able to establish a world-leading limit on light vector mediators. Why? Because as you see here, light vector mediators goes up very, very fast. So if you go to a very low threshold, even if you are not able to see sevens, you can be competitive to constrain some beyond standard model scenarios. And the other point is that a few months ago, CONI has an upgrade with a new detector, which is called MCM. It's essentially 16 skip per CCD, each of them of ½ gram, so in total we have 8 grams. And I don't know if you know the guy over there, because probably you don't know that Martin Carla is the spokesperson of CONI. So there are a lot of people here organizing this school that they are scientists making the science you are learning here, right? It's the same people. Okay, so we expect for this detector to enhance the sensitivity of CONI for sevens and all the others beyond standard model scenarios. The other experiment is Atucha 2 in Argentina. This is the reactor. It's a 2 gigawatt, the half of Angra. Yes, in the power is the half, but we are inside. It means we are 12 meters away from the core, just 12 meters. You know, the flux goes like 1 over the square of the distance. So that is the reason why the flux is a factor 3.3 better, yes? Okay, now we need to go inside. So in order to do that, we need first to dress up like a minion, and then passing through this door, you are inside. Inside means this is the reactor core. It doesn't work, but the blue one. And we are there, 12 meters away from the center, 8 meters away from the wall, right? And how the system looks like this, here. We don't have 16 tons of yield. And that is the reason why in Kony we have a better background. You will see it. But it's a very, very small setup, you see, in comparison with all the other setup you have seen this week. Okay. Okay. How the detector looks like. Again, it's just a piece of silicon, 2.5 grams, inside a copper box, and this is inside a vessel because we need vacuum to operate this detector at 140 Kelvin degrees. And around we have a passive shielding, but just 5 centimeters of lead and 5 centimeters of polyethylene. That's enough. It's not enough. That is what we have. We would like to have more. Okay, this is the first image we have had inside. And I would like to see how it looks like in this beautiful place. It's like, okay, nice. I would like to be over there because here with the light I cannot see. But each of these is a different particle. Yes, the straight line are neutrino, and the others could be produced by electrons who release the energy that they take from a gamma, for example. And we expect for any of these to be a neutrino, to be an electron produce the interaction of a neutrino, right? So you need to look inside this picture because essentially we take pictures to the particles, right? And then you need to go inside and apply quality cuts in order to extract from them the information you are looking for. This is the Eliana's PhD, also Pedro's PhD in Kony, a lot of people working on this. Okay, where we are now and where we expect to be in the future. Right now, Kony, Atucha are not sensitive to 7s, right? The black line represents the state of Atucha. It means that if we run as we are, in 2 years we will close to 60% confidence level. Not enough to say something regarding 7s. But if we increase the mass, yes, and we have planned to do that as Kony already did, now they have 8 grams instead of 1 gram of a keeper. And we reduce the background and we have 1,000 kilograms of lead waiting for us inside the nuclear plant, we can go up here. And if that is the case, in the best scenario, which is not conservative but is good, is possible, the blue line means that in 2 months, under that condition, we will see 7s with 3 sigmas, right? Okay, first we need to reach that condition. Increase the mass and decrease the background, of course. Okay, these are the result, the main result up to now from Kony and Atucha collaboration. On the left, you have the result from Kony, which is essentially the event rate observed as a function of the energy when the reactor is on and when the reactor is off. The main difference between neutrino and dark matter is that we can turn the neutrinos off, right? And that's the reason why we have a measure of the background. We can subtract that background. And then just to see if the difference is or not compatible with 0, essentially. On the right, you have the result from Atucha. And in the inset, you see two different spectra. The blue one, because is from the run 2022, and the other one is from 2023. We learned how to decrease our threshold, and now are in 40 eV. So, but in the case of Connie, we have already 15 eV as a threshold. You can ask, okay, why 15 if you are talking about 1 eV? Okay, because there is dark current, there is other event that populate the CCD, is our background, and we need to get rid of that. We work a lot to understand how to apply very efficient quality cut in order to reduce that, and that is the reason why we can go to 15 eV right now. Okay, but you see here a huge difference between backgrounds. Yes, a factor 7. Okay, but do you remember I said Connie has 16 tons of shield, and we have in Atucha just 200. However, because of the flux is a factor 3.3 and the mass is a factor 4, the sensitivity for beyond standard models is in some cases very, very similar. But the best part of this history is that Connie and Atucha are essentially the same people. Yeah? And we are all here teaching you about neutrino and dark matter. So what we did is a joint effort to use this data to constrain new physics. And that is the case of many experiments looking for 7. Even when you are not able to see that interaction, you have data good enough to say something regarding new physics, like the vector mediator that I showed before, right? So let me talk about how we combine this data in order to get a good result. Let me know.
My question is, why don't you put a shield around Atucha? Like, wouldn't it improve significantly your results?
You are talking about shielding the full reactor? I don't.
Or just building like a little light castle around the detector itself?
Yes. We have planned to do that. We have 1,000 kilograms of lead to do that. But inside, let me go back to that place. If you are here, you see the detector over there. This wall, yes, is 8 meters away from the uranium. And the space here is not too big to put, let's say, 16 tons. And when you are inside the nuclear power plant, you have a lot of rules, yeah? And they are very important, and you must go through of them. So it's not easy to put 16 tons of something inside a nuclear power plant. However, 1,000 kilograms, yes, that is possible, and we have already 1,000 kilograms of lead very close, 200 meters away from that detector, waiting for us, or for the people working at the nuclear power plant, which is the most important part of this experiment is the people working in there, because they help us a lot. As part of their work, they plan to put more lead around, and then more polypropylene also. That is possible, yes, and we want to do that.
Okay, thank you.
Okay. So, the difference coming from two facts. We are in Atucha inside, but we are outside in Connie. In Connie, we have 16 tons, but in Atucha, we have just less than 1 ton. However, we can compensate this because of the flux and the mass of the detector. So let me go now to one specific model. It's not neutrino. Yes, it's not neutrino. We need to wait a little bit more to see neutrino with this kind of technology because we need more mass, better shielding. Okay, but there is a very well-motivated particle, which is the milli-charge particles. Milli-charge particles, they are, if they exist, they looks like an electron, but the charge is 1,000,000 times smaller, right? Why? Because it's just a factor 10 we had seen. Why we wouldn't see? Just because the charge is too small. Okay. This is the other part of the statistical course. During the statistical course you have taken this week, we were addressing the problem of how we can deal with data to produce an upper limit and how we then can build up an exclusion limit, right? But the other side is we need a machine that for a given parameter, mass and cross-section in the case of dark matter, and mass and electric charge in the case of milli-charge particles, how many events we expect in our detector, yes? To run this calculation, you just need to do first this integral. You must integrate the gamma flux, yes, which in the reactor is well described by this equation over here. And then you need to multiply this by the production cross-section of milli-charge in a reactor. Why we expect for the milli-charge to appear there? Because there is a channel which is something like a Compton-like channel able to produce milli-charge. So following the lepton pair production formula, this one over here, we can calculate how many milli-charge we expect depending on the number of gamma ray we have. And reactors are emitting a huge amount of neutrino, and of course in the nucleus are a huge amount of gamma. So if you have a huge amount of gamma, you have a lot of opportunities to create milli-charge. Let me say that milli-charge is also a candidate for dark matter. Okay. We multiply, and at the end, we have the flux of milli-charge we expect in our detector. Of course, here we have the factor 1 over r squared. Yes? Okay, the other side of this calculation is here. What we need to compare with the upper limit you all learned to calculate during this week is the rate produced by the rate of event we expect in the detector. But now we need to take into account the detection cross-section, right? And for milli-charge particles, a very, very new article, in fact, is on archive, but not still published, will be published soon. These guys describe how we expect for the cross-section of a milli-charge particles as a function of the energy recoil. And you see, again, a very important reason to have a very, very low threshold detector. Why? Because here, around 15 eV, there is a peak, what we call a plasmon peak. It's like a resonance in the silicon produced by these particles. So, if you have a very low threshold, as the one Connie already has, 15 eV, you are able to take advantage of this peak, which of course enhances a lot the probability to detect these exotic particles, if they exist. In the case of Atucha, we are now in 40, so we are not able to take this peak, but we can take the second one. So, we use this cross-section to calculate over, with the formula you are seeing top on the left, the rate as a function of the energy. Yes? It's just the product of this cross-section by the flux of neutrino, of milli-charge that I described in the previous slide, right? So at the end, we can calculate the number of events as a function of two parameters, the mass of the Milli charge and the electric charge of the Milli charge, what we call epsilon, which is a fraction, of course, of the electron charge. So, what is the result of doing this? What you are seeing here. It means that two experiments that are using charge-coupled devices to look for neutrino are not still able to see coherent interaction, but we have data to produce the world-leading limit for Milli charge particle, which is a very well motivated candidate for also for dark matter, in 6 orders of magnitude. You see here 6 orders of magnitude, and this is the previous result from Texono in 1999. How we do this? Just to connect both parts. As you learned today, what we did is, using this formula, we put one mass and one epsilon, which means some possible charge for the Milli charge. We calculate the number of events we expect, the rate, and then we compare this with the 90% upper limit we have after analyzing our data, right? When we match them, we have this line over here. Sorry about the dashed line and the other lines. I forgot to put one more slide to explain why we have two different limits here, and just is because you get a better limit if you consider that you have gamma rays, prompt gamma rays, the one were produced by the decay of uranium, the fission and then beta decays, but you must also take into account the gamma that are producing after the first interaction. Yes, Guillermo, one of the guys in both collaboration, was calculating this by using GEM4, and he discovered that we can improve, as you see there, the cross-section if we take into account all the gamma rays, not only the gamma coming from the first decay. Okay, my last point here is that what we need to do this kind of limit in dark matter, neutrino physics, Milli charge, whatever, we have some exposures, reactor on and reactor off, you said here, all the time gamma grams per day, because of course it depends on the size of your detector and the time involved in measuring, and we need a model to predict which is the number of events you expect, and then when you have the upper limit coming from your experiment, you just need to move the parameters around to reach that upper limit and set this beautiful constraint or world-leading limit. So my point, I am done. My point here for you is, we are in South America, and in South America we have two experiments using the same technology that Sensei used to have the best limit, exclusion limit for dark matter in the range, you know, from the MEV light dark matter. And we are running experiment in Brazil and in Argentina using that technology, and we can use the result to publish the better exclusion limit in one of the particles that the community is looking at, like a very important candidate. And we expect all to do the same with sevens, and in the case of other models, even if you go to the plot where you see as low as the energy, the higher the number of events you expect, we are able also to constrain other kind of particles. Neutrino magnetic moment, light vector mediator, and so on, right? Okay, that is my last slide, just for you to see how an image looks like and contemplate this, because it's very, very beautiful. And I would like to take the 5 less minutes to discuss with you about each slide, because I know that it's a lot, but I would like for you to go understanding all of them completely. That is the aim of my talk. So let me know your questions.
Questions?
Hi Dario, thanks for the very nice talk. It's very exciting to see the results for experiments based on South America. But I have maybe a very direct question about the light vector exclusion plot from Connie that you showed. How exactly are you parameterizing what you're seeing with these light vector mediators? Because then you, depending on your model, you have different couplings that might be flavor dependent, or they can have the same or different signs.
Right.
With respect to the standard model weak charge contribution. So what exactly are we seeing in this kind of plot?
Okay, yeah, thank you for the question, because there is something here that is missing, and this plot, you can go in detail over to this plot let me show you the reference, just for you to go in details about the calculation, and here, yes. But first, you see that all curves touch each other over there. That is because we normalize them. Why? Because in this plot, we are not interested in knowing which is the amount of event we expect. And that is also the reason why we have here, arbitrary unit, you see? Mm-hmm. This is just to see how it grows when you go to lower energy. That is the first point. The second point is, of course, in order to get all of them closer for the lowest energy, you need to change, you need to play around with what you said, with the coupling, for example. In the case of the light vector mediator, what we set here to see what you are seeing is this. Is a mass for the light vector mediator equal to 1 EV and a coupling close to 2 × 10⁶, right? Under that condition, you get this, yes? And in fact, if you see, this number is very, very close to the limit that Connie has, because for 1 MeV, for 1, no, it's lower than this. But this is very, very flat then. Yeah? For 1 EV, you have 1 MeV, you have a number very close to this. So yes, we need to play around this, and that are the parameters we need to move to see when we reach the 90% upper limit we established with our experiment. So again, for all of the others, the caption of this figure in that paper has the number we use. But it's just to see how they grow up, nothing else, right?
Okay, thank you.
Hello.
Pedro,
Dario.
thank you for your slides.
Okay.
Few of these coming from...
So just like that, this plot on the right that you're showing us, there is a lot of beyond the standard model
Yes.
predictions and so on. So are there any standard model processes that could compete with neutrino nucleus interaction in this
Yes.
energy range?
Yes. Yes. And that process, the one is there because of a standard model physics, is for us a background when we are looking for beyond standard model. And the name is sevens. Sevens is our background when we are looking for this. Here, you see the black line, standard model neutrino nucleus, that is for the coherent elastic neutrino nucleus interaction. So there is a new era when you have detectors high enough or good enough to see sevens with a very, very more uncertainty. When that signal, we are looking for this signal, after find it in the future, we expect for the 7 to become our background. And then probably we can discount background coming from 7 and go forward. Up to now, we are still looking for sevens, but in the very, very low energy regime, you can forget about sevens because there is another candidate from beyond standard model that produce even more event than 7 in your detector if you have an skipper CCD, right?
Further questions? Yeah.
Thank you. I always had doubts with the quenching factor estimations.
Yes.
How would you know what is the correct model? Or when will you know that? Or
That
how?
is a very, is the kind of question that
You always fear. Yes, I know. But it's I always see the models and
yeah.
I mean,
I will
if you
address
do-
your
if you
question
didn't-
anymore.
If you didn't put both curves, I wouldn't ask this. So
No, you're right. This is the situation with the quenching factor. It's not just a problem for us. It's a general problem. We don't know. We still don't know what is the response of a nucleus with less than 500 eV. Is there the possibility for those nucleus that they do not produce any electron ionized? Yes. And in that case, it doesn't make sense? Yes.
okay.
But what we know, because it has been measured here, you see, until 700 eV of recoil energy, the quenching factor was already measured. And we all know that Linhart model is not a good description in that energy range. So Linhart is the blue dot lines. Is blue or is another? Okay,
The one,
you know, I am
in
colorblind.
colors.
It's blue, thank you. The blue line over there. Yeah, here Linhart is a good approximation, but over here we cannot use Linhart. So we plot Linhart just for the sake of the simplicity, but we don't know that. We know Linhart is not correct in this regime. But if you take these numbers, you can take an approximation of this, and you can describe how the quenching factor change depending on the energy, following this curve over here. And this paper from Youssef from Mexico, he developed a very nice model to explain how we expect if we go lower. And as you see, below, let's say, this is energy recoil, right? No, it's not the energy we detect. Energy recoil, we do not expect signal. But someone must measure this. And if any of you is interested in doing this measurement, please call me. Please send me an email. We have a lot of idea to how to use a skipper CCD in order to improve this measurement. We have reactors, we have a skipper, we have ideas, we have all to perform an experiment here. And you know the impact of the result. If someone measure the quenching factor below 500 eV, all the community looking for event in the very low energy regime must use that result. The community is expecting for you to produce that result because the result, as you pointed out, depends on this. Yes.
Okay, count me as a volunteer then.
Another question? No? So let's thank him again.
You're welcome.
And Dario, also thank you so much for coming here and for being here. I'm also, as a Brazilian, I'm quite proud of the South American community for doing this great science. And I guess now we can be really competitive with the US and European communities. So
Yeah.
we are quite proud of this. Thank you so much. Let's thank all the speakers again. And we move to coffee break.